as I say, I'm just going to do this is so if you want to see something new, flashy, visual, go to the system model or talk next door. I'm just going to talk about nuts and bolts, but hopefully I'll cover stuff that's in a little different way, or maybe a way you haven't thought about before, and hopefully everybody will learn something from what I'm presenting here today. Though it won't be, I don't promise any flashiness. So, okay, so first I'm just going to start with this. I think now we have decent resolution. I can make this bigger. So this is a graph, and so I'm going to talk about numerical mathematics, and I think numerical mathematics is really a part of the core of what Mathematica and the Wolfram language is. It's sort of the glue that binds everything together. And this is sort of just a crude graph of things in numerical mathematics. Sort of the root of everything is arithmetic, and that's where I'm going to start today. So arithmetic, and so I'll sort of go through and talk about various of these components. I'm going to give very few examples. I'm leaving that sort of the better, more flashy examples, the more exciting stuff will be given in talks later during this conference that I'll advertise at the end of this talk. So I'll just talk about pretty much nuts and bolts, but I think I enjoy doing this because I think there are a lot of things people don't realize how the system works, and it's so fundamental to the system. Once you understand these things, everything else sort of fits into place. Or at least that's my view of it. So I'll start with arithmetic. I'll eventually go to numerical evaluation. And I'll talk about sort of the interrelationships between symbolic computation. Notice symbolic computation has a lot of things going out of it here. It depends on the arithmetic, but it affects all of the numerical things we do in Mathematica in some way. And that's really an important part of what makes Mathematica unique as a system in terms of doing numerical computation versus other systems. So before I even get started with the arithmetic stuff, I'm going to talk about sort of the basic design principles that we try to put in numerical functions in Mathematica. And I think that's an important part of Mathematica, is that Stephen has been really good about imposing design principles on Mathematica. That makes what the whole language, that's why we're able to expand into these other fields, and people are able to sort of get it, because we try and use the same design principles throughout. And so numerics has some particular design principles. Okay, so the first one, I think this is really, is that big enough to see in the back, or should I make this a little bit bigger? Okay, I'll make it bigger. I'll go to 200%. So that's about as much as I can handle. So because if I can't see anything, I can't talk about it, right? So, okay, so the key thing is that functions are task-based. So you want to solve a differential equation, you go to ND-solve. You don't call a program called ODE15S or various things like that. So you think about it. You want to find a root. You want to find a minimum. You want to end minimize. You want to minimize. So everything is task-based. So within that, you can select particular algorithms using method options. So all these functions have these method options. You can go very deep in the method option to select particular algorithms or even aspects of particular algorithms. But what we try to do, and this is what a lot of my work ends up doing, is figure out, okay, so given a problem, and Mathematica typically has a symbolic specification of a problem, like a differential equation or a root finding problem. It's usually given symbolically. So we look at the symbolic form of the problem, say, okay, can we pick an algorithm that's going to work well for this? And we don't always get it right, in which case you should be using the method option. Or we should do better. But we try to pick an algorithm that's appropriate for the problem you've given us, and then we just try to solve it as well as we can. So a big thing that Mathematica does, and this is where the symbolic computation comes in, is trying to analyze the problem type. What kind of problem do we have? How are we going to solve this? That's where we spend a lot of effort doing. I mean, a big part of effort is putting in the basic algorithms to have available, but a big part of it is choosing what algorithm to use. Okay, another thing is output from one function should be easily used in other functions. I think Stephen showed like an interpolating function this morning, or a time series thing. The idea is those are sort of interoperating in the system. You'll be able to work with them easily. And specialized data structures have interfaces that integrate with the rest of the system. Okay, in operations based on input values or data, we try to return a result based on the precision of the inputs. So if you give, a number with 20 digits, some computation will come out and maybe the result will have 18 digits. But in many cases, those 18 digits will be based on how much precision was in the input and how much was lost in the arithmetic. Now there's exceptions, and I'll show that. But typically, so if you give exact in, typically you'll get exact out. If the symbolic computation is done, approximate in, approximate out, according to how approximate it is. Okay, and with machine numbers, those are the hardware numbers that are fast. They don't track any precision. You'll get machine numbers out. And we have arbitrary precision input, and I'll show you how that works in just a bit. The arithmetic, we try to propagate precision along with the arithmetic operations using something called significance arithmetic. Okay, and then in various functions like ND-solve, find root, find minimum that work with functions, you can control the quality of the solutions by optional arguments or actual function options. Okay, and there's a command N that does numerical evaluation that's fully adaptive, and it accepts target precision. I'll be showing that pretty soon too. And commands work with things like working precision, precision goal, accuracy goal. And that's a way you can say what the quality. We have defaults, of course, but it allows you to say how good a solution do you want. How much do you want Mathematica work to get a decent solution? Okay, and then there are underlying data structures, and full interfaces are often made for those that are efficient. An example of that is projects I've worked on in the past, packed arrays, which is sort of an array representation of lists that's been allowed people to do stuff like compilation to C. Sparse arrays gives you access to sparse linear algebra. Again, that's integrated in the whole system. So it's not just an isolated optimization that we use under the hood. It's something that you can use as well. So those are the basic design principles. Let's go to arithmetic. Okay, so again, arithmetic seems really simple, right? Why bother talking about arithmetic? But this, again, is something unique about Mathematica. So we have arithmetic for 4 types of numbers: integer, rational, real, complex. And we keep exact representations like the square root of 2. So if you enter the square root of 2 in Mathematica, it stays as the square root of 2. Now, some radicals may simplify themselves into other forms, but it stays as that symbolic thing that really represents the exact square root of 2. It's not 1.14, whatever. Okay, it's really the square root of 2. Now, you can get a numerical approximation of that. I'll be showing you that soon. Okay, and then there are, again, more subtypes within the various types. There's machine reals, machine integers. Those are the ones that the hardware can handle and work fast. But you extend beyond that. We go to numbers with thousands and millions of digits of precision, or integers with millions and millions of digits. And on this machine, which is a 64-bit machine, I can exhaust the memory of the machine before I'll run into the size limit of an integer you can have on this machine. So it's really limited only by memory now. And we use the GNU multi-precision for arithmetic. And then, so this is the really important thing is at the bottom here, of course. And I'm just emphasizing this again. I've already sort of said it before. Mathematica has a coercion model. And this goes from arithmetic, but this basically goes throughout Mathematica because the arithmetic is everywhere in Mathematica. Okay? If you have exact in, it gives you exact out, unless the command is specifically something that does numerical approximations. Okay, and again, if it's not exact, the precision of the result is very typically based on the precision of the inputs. Okay, and machine numbers, okay, and this one is important to keep a bead on. They're fast, they work really well in many cases, but they don't track precision. When we can't track the precision, the hardware arithmetic doesn't do that. So we consider those to have less precision than any other numbers. So if you're using machine numbers, they sort of, so to speak, infect a computation. Everything will be with machine numbers. So if you really want to get significant results, you need to avoid machine numbers completely. Okay, and then arithmetic operations thread over lists, and this is the way to get speed out of Mathematica. I'll show a really quick example for that. And this applies generally to computations in Mathematica, not just the arithmetic. Okay, so let's keep moving forward. So here's a simple example. Exact in, exact out. So if I do square root of e, notice that this has been simplified, but it's still an exact result. So Mathematica puts things into a canonical form. It does some arithmetic, but it doesn't change. These are exactly the same number. Okay, there's no change except in form being made. But you can still do computations with that. For example, I can compare if that's greater than or equal to 4 or not. And that's a computation which is basically effectively like a proof in that case, because it's exact. It's actually exact numbers. When Mathematica can't resolve it, it'll give you a warning about not being able to resolve that inequality. Okay, so now let's look at actually precision inputs. So let's start with a number, say 0.9999999 with lots of nines. If I enter enough digits, Mathematica will just automatically realize that you mean something with more precision than a machine number, which only has about 16 digits. And so I've got a precision. So I can actually look. There are commands that allow you to investigate this. So this has 30 digits. So precision is a measure of the relative error in the number. So this basically means that this number has, the error in this number is roughly 10 to the minus precision, so roughly 10 to the minus 30th. The accuracy is an absolute error, so it means it's plus or minus 10 to the minus 30th from 0. I mean, from the center of the number in absolute terms. This is relative terms, absolute terms. And then, so in precision, if I multiply by a constant, it doesn't change the precision because the relative error is exactly the same. Particularly if I multiply by a power of 2, since all the numbers are binary in representation, that doesn't change anything except it changes the exponent. That's all it changes. So it doesn't change the precision. But it does change the accuracy. It changes the absolute error. By making it bigger, I make the absolute error bigger. So that's sort of the quick way of thinking about the difference between accuracy and precision. And for most computations, in fact, not almost all, but a big percentage of computations, the thing to think about is the precision. What's the relative error in the numbers? There's some cases where absolute error is going to be very important, but most cases it's relative error that really ends up having the most effect on a computation. Okay, so again, I'll emphasize the error interval for that number actually above is between this, and it's got that length. Okay, so let's do some arithmetic this. Let's make y equals 1 minus x. So now I get a thing with 0, okay, because, and notice it only prints the 0. It doesn't print any more digits. Okay, what the Mathematica is basically telling you there is it doesn't know any significant digits, okay? Because if I subtract 1 from this, well, the last digit is between 0.85 and 0.95. It doesn't really know with any significance whether that's different from 1. So now if I look at the precision and the accuracy on this one, okay, so it has no precision, because I don't know if any of those digits are right. But what I still do have information about that number. Okay, and that's why it shows with this exponent of minus 10 to the 30th. I know that this isn't going to be, once I subtract 1 from this, I'm going to be within the interval basically 0.5 times 10 to the minus 30th, plus or between minus 0.5 times 10 to the minus 30th and plus 0.5 times 10 to the minus 30th. And I'm going to be in that interval, so it's really close to 0, but it doesn't get any closer than that. And that's what the accuracy, so in this case, when you're near 0, that's when accuracy becomes a fairly useful measure of what's going on. Okay, so let's see. I think that's it for that example. Okay, so machine precision. So now if I take the same number and I take y as 1.0, okay, now 1.0, when I enter a number with just a few digits or 1 or 2 digits, it's interpreted by Mathematica to be a machine number. I can also use, I'll show you, you can just use n with one argument to make sure you get machine numbers. Okay, so now the precision is actually given as this special value, machine precision. So that tells you you're working with machine numbers right away there, okay? And it has that accuracy, and the accuracy will change with machine numbers. And there's also a test. You can tell whether something is a machine number or not too, which is machine number q. Okay, so now if I do arithmetic with those, what happens is everything's coerced to machine numbers, okay? Because this is a machine number, this is not, but we go to the least precision, so this gets coerced to machine number, which actually gets coerced to 1 as a machine number. So I take 1 minus 1, and I get exactly machine 0. Okay, so you've lost all significance in that problem by having machine. But in many cases, that's just fine. And your computations will be fast with machine numbers. And that's what allows Mathematica to do a lot of stuff really fast. But if you need more, you would want to coerce that 1 to something else. And again, I get machine precision. And then this is the accuracy near 0. So machine numbers are closer near 0. So I know I basically have 307 digits of supposed accuracy. So it really hasn't kept track of the accuracy. That's just based on the property of that number alone. OK, so finally, let's go to so that's what I'm going to say about significance arithmetic. Let's go to the threading over lists. So this is an important feature in the language. So here I've got a scalar, which is b. I've got a, which is a vector, and c, which is effectively a matrix. And I've chosen them to be a commensurate size. So if I take b multiplied by a, what it does is it uses that same coercion model. So even though a had some exact components, b was inexact. It was a machine number. So everything gets coerced to a machine number. So I get a vector of machine numbers out. So it basically multiplies b by each component of a. So that's like scalar multiplication of the vector. That's kind of the way to think about it. OK, I can also do vector addition. I can add that to a, OK, itself. And again, those are all going to be machine numbers. And I can also add a vector to a matrix, which is a plus c. Now notice in this one, because c was all exact and a had some exact components, only those components which had machine numbers were coerced. Everything else is kept exact. So Mathematica is consistent at every level of the list with the way it converts. It coerces. OK, so the listable stuff and being able to do vector addition, so if you can write your programs to sort of thread over lists, you can get stuff done really fast. And here's just a quick example of using the compiler. So I'm taking this function, which is, I take different values depending on whether I'm greater than, less than 1. OK, and I'll put in a test function, which I want to generate now to do that. OK, and then I can test how fast does that work. OK, so that takes 0.065 seconds. And that's 4 times slower than just doing addition. But considering the addition is done by special vector functions in the hardware, that's pretty good for something that actually is evaluating an if in Mathematica. So if you want code to run fast, OK, a way to do it is to use listable operations, and this runtime attributes as listable in the compiler can often be very, very fast. So, and if you want to know more about that, you'll ask me later. I just don't have time to cover that today, or we won't eat.
Slower if you hadn't put that in listable?
Well, if I hadn't put in the listable, it just wouldn't have worked, because the compiled function is expecting a scalar real. And without the listable attribute, it would have just said, oh, that's not a scalar real, and it would have done normal evaluation, and it would have been really slow. Try it. You'll find out. And if you didn't do the compilation target goes to C, it would have been somewhat slower, but not that much slower. OK, so let's go to numerical evaluation. And this is sort of, so the command n, to me, the command n in Mathematica is the command that has the smallest name with the biggest stuff. OK? And the person who's really responsible for what n done is Mark Sfronio, and who's not here this year. But there's a lot of work that goes into this. And when you use it, it seems obvious. Well, I want to convert the square root of 2 to a number. You just do n on it, right? And it works. Well, there's a lot behind that. It's kind of neat how it all fits together. So first thing is, if you just use n with one argument, it'll use machine numbers. So if I do n of the square root of 2, it'll give me 1.141, to roughly 16 digits. But n of x per p works much harder to try to get a result that actually has precision p. OK, so it adaptively works to try and get a result with the requested precision. The times it'll fail to do that is when the result or some of the sub-results it gets are near 0. And 0 can't be represented with a certain precision. And that's when you might want to ask for accuracy. But if Mathematica is not able to get the precision you request, given exact inputs, it will always give some kind of a warning message. OK, so let's take an example of n. And this is just this is Stirling's approximation of the factorial function. Just a simple way of writing it. So let's enter this. So this, again, is something that just, if I give it an exact value t of 100, it just evaluates, and I have an exact thing in terms of representations and actual big integers. Okay, so now that's something I can do n of. So n quickly finds that. Okay, and then I'm going to compare my operation. I'm going to use the gamma function for a reason. Gamma of t plus 1 is another equivalent to the factorial. I'll compare with the error. So in this case, this approximation is 0.008 away. So it's not a great approximation, but it's, and now notice I'm measuring this in terms of relative error. If I did it absolute error, the error would be on the order of 10 to the 153rd, which is big, but so that, I mean, that's why typically, you know, whether Stirling's approximation is a decent approximation, if you measure in absolute terms, it's going to be hopeless because the error is always huge. But if you measure in terms of relative terms, you can actually see the approximation is doing something for you. Okay, and that's why relative error is usually the measure you want to think about. Okay, so we can get that error with actual significance. So we can evaluate that. And so this is saying I want to evaluate this error term. And notice I'm using ST instead of NST, the numerical value of ST. So this is an exact expression. So n goes and adaptively recomputes this until it actually gets a result with significance of 20 digits. So that you can pretty much trust. It's not as provable with interval arithmetic, but when you're using enough digits, it's generally, you know, pretty assured. Okay, so that error term is good. Now let's try it for a much bigger number. Okay, I'm going to cheat a little bit. Okay, I want to try this for 1,000,000 factorial. See what happens. Okay. Well, first I'm going to do a couple of things. So if I try and evaluate this term in terms of exact integers with 1,000,000 factorial, this integer is going to get huge. Okay, it's going to fill up my screen. It's going to take up my memory. And this poor old Mac is, you know, this 3-year-old Mac. I think they might have to buy me a new one of these days. But it still would have trouble with a brand new Mac. It's just going to take up too much memory. So what I'm going to do is I'm going to use a nice trick. Okay, and I'm going to say only evaluate this when n is a real number. That won't affect any of the adaptive stuff in the n command, but it's going to replace when it does a real number. Then it evaluates, and this evaluation will be relatively quick, rather than trying to actually work with the big integers you'll get. And again, I'm doing the same thing for my gamma thing too, because gamma would evaluate evacually and would actually expand in terms of the integer for an integer n, because it is an integer. So we don't want to do that. So let's, because we definitely wouldn't get dinner if I tried to do this the other way. So let's try this. Now, here's a neat one. So here I did n with no precision argument, and I got this number. Do you think that's a machine number? No, the largest machine number is this, 10 to the 308th. So my exponent's just a little tiny bit bigger than that. So, but let's compare this. So what Mathematica has done seamlessly and automatically is it's just converted to arbitrary precision numbers with significance with an extendable exponent. And this exponent can be absolutely huge. Okay, you can check what the exponent is. I won't do it here, but if you type in $max number, it'll tell you what the largest exponent can be. So this is not a machine number. Okay. But we can still do the basic stuff, okay? But this actually tells me I don't have any significance in this result. Okay, so I want to know what the error term is. And this is where the n with the precision really comes in handy. I say, I want to get that to 20 digits. I want to know what is the real error term. That gives me the same thing, okay? But this is actually got 20 digits of precision, of precision. So I know what the size of the error term is. And this might look familiar. The other error term had exactly that same coefficient, 8.333. So I'm going to speculate now, well, the pattern of the error, and you could actually look this up, is something like the OR form 20 to the t. So let's add in this term, redo the error. And notice we get many orders of magnitude less error just by adding an extra term to the Stirling approximation. So by looking at the significance, I was able to just, quickly, it doesn't always work out so nicely, but I didn't have to look this up, look up this term to guess what it was. And then, of course, I would go and test further to see if that really was a reasonable hypothesis or not. But that's an example using the significance arithmetic, which I think is kind of a neat. And using that trick to prevent symbolic partial evaluation is often very useful if you get results, intermediate results that might be really, really big. OK, so let's go quickly to linear algebra. So linear algebra is sort of one exception to the model. It does supports linear algebra, and of course linear algebra is key to a lot of the algorithms Mathematica has. I mean, numerical algorithms, and we use basic linear subalgebra that are super optimized. We use an Intel math kernel library, which gives us speed for machine numbers. And we also have sparse matrices represented by sparse array objects. And I'll show just a couple examples which demonstrate the linear algebra. There's one. Okay, so let's take an example, the Hilbert matrix. If we do this, I'll look at the smallest. This is asking for the smallest eigenvalue of the Hilbert matrix. This actually, notice that I had the Hilbert matrix comes out exact. Again, exact in, exact out. And that's why it took so long. It took 7 seconds, but I actually have an exact result in terms of these root objects. Okay, so that's a truly exact result. Now, if I made the matrices much bigger, we might never get dinner. But I can take the numerical value of that instantly, and that's going to be an accurate numerical value because it's based on the root object, which has accurate stuff. Now, if I just did this, so notice if I do n of m first, okay, this takes the numerical approximation first and then does the eigenvalues. Well, I'm not doing so well. But this is the Hilbert matrix is a classic example of a poorly conditioned matrix. So this computation is poorly conditioned for machine numbers. So that's a limitation of doing linear algebra with just plain old machine numbers. The advantage of it is it's super fast, but there are cases where it just doesn't work. Now I can do 50-digit arithmetic. Okay, so here I take n of m50. Now linear algebra is an exception. It doesn't try to compute the significance as it goes because all the linear algebra commands are designed to track error. So we keep all the digits in this. So this actually shows 50 digits, even though significance might be a bit less than that. And the reason is we get too much cancellation with the significance arithmetic, and all the linear algebra theory is based on sort of tracking error. So we know this has some reasonable error. It's not this good, but you notice it is getting the first several digits absolutely correct. Okay, so and we can quickly test the relative error against this. And so even though we use 50 digits, only about 3 digits are correct. So it's a pretty badly conditioned matrix. Basically, for Hilbert of n, you need n digits to even get the first bit of this. So let's take a small example. Here's a relatively small sparse array. This comes from our matrix collection. I've actually cheated and imported it ahead of time, so we don't have to wait for the server. So here I'll take a random vector. So if I just solve this with linear solve, even though it's a 4,000 by 4,000 matrix, it's solving it in 0.05 seconds. It's taking advantage of that sparse structure in it. Now I can convert it to using normal to a normal matrix, and I've done this so that I'm taking the ratio of the size in the matrix in sparse form versus dense form. So it's 307 times smaller storage in the sparse form than it is in the dense form. Now think about going to a 40,000 by 40,000 matrix. You could do it in sparse, and this machine would die in the dense form. And again, the timing is a little bit good. There's some overhead for doing the operations of sparse, but as you see, this is taking a lot of time to do the full dense thing. So it's basically a factor of 100 faster to use the sparse algorithm than the dense algorithm. It's huge. And we can look at the error. This actually makes kind of a neat plot. The error is tiny. So you don't lose any real accuracy by using the sparse because we have direct methods as opposed to iterative. Now an iterative method would have more error, might be faster, but it would have more error. By default, we use direct methods. So I think that's an example of, but notice the sparse array, in terms of using it, this is the thing that's important. I just use linear solve, nothing different. It's a sparse array, system doesn't care. It just uses the right algorithm. We try to do that as much as possible. Okay, so now I'm getting down to the last couple of minutes, last couple of examples. So functions based on functions. Again, they're task-based. Output can be used easily. Errors controlled by options, accuracy goal, and precision goal. I'm repeating myself. But those are really important points. And we can also use things like evaluation and step monitor to see what's going on with the method sometimes. And there are frameworks that allow you to sometimes plug in your own methods. It's not always easy to do it, but we do provide the possibility. So let's look at, I'm going to look at a couple of two examples left. This one is differential equations and root finding. So I'm talking about interrelation of commands in Mathematica now. So this is, I've got a thing, and so I'm solving a diagonal system. X prime equals y prime equals -1, y to the 10th over 10th. So let's solve this system. I'm doing, oh my. I obviously need to clear something. Maybe it's T. See, I should have, there, that's happier. Okay, so this is so now as I move this slider around, notice I have just a normal dynamical system here. But once I get to a certain point, notice it goes along a line and then it repeats itself. This is something called sliding mode. And I gave it a discontinuous vector field. So that basically the vector field here is pointing up, and the vector field here is pointing down. So everything gets sandwiched into so-called sliding mode along that. Now, without being able to detect the root of that crossing, which NDSolve now does automatically as of version 9, we wouldn't get anything for this system. Okay, and that is what happens if I do this, which I'll do really quickly. Okay, so this one I purposely start in the center. Then if I try to go out, as soon as it hits that, oh my gosh, yeah, it goes pink, and then I get some oscillations. That's what happens if you don't try to detect that. It's a complete disaster. Okay, so fortunately, we don't do that by default. I had to specifically turn it off. Okay, so let's look at one more example. This is it, and then we can go to dinner. Differential equations and optimization together. So here I've got some data, which I have to admit I artificially produced. So let's say I've got a wall and I've put a temperature probe in the middle, and I know at some time I set the temperature on one side of the wall to be 20 degrees, and the other side at 0, and I put a probe and I measure the temperature in the middle over time. That's what this data gives me. With natural error, would you have a probe? What I want to do is I want to find, well, what's the diffusion coefficient of that wall? How good is the insulation, say? Okay. So I set up something called parametric NDSolve value. I've set some specific options to make the parameter estimation more stable. Now this parametric function, this is a differential equation function which depends on a parameter A, which is the diffusion coefficient I'm eventually trying to find. So I can plot this function, and something the parametric function provides neat. This again is something useful. Okay, parametric function is another function. That's a function that produces a function, an approximate function. I can plot not only the function as a function of t, but I can plot its derivative as well. So it's automatically computing what are called sensitivity computations to do that. And with the sensitivity computations, I can just give that as a model to the function find fit. This takes a little while because it's actually solving a bunch of different equations. Because of the error in different equations, not able to be totally happy about the result. But let's look at the result and see how good it looks. Well, that looks like a pretty good fit. At least I'm happy enough with it. So that's sort of, those are two combinations of commands. There's going to be a bunch more, okay? And in a summary, I'll go through a few things. I've shown you how numerical computations works. So the main themes are in operations based on input values or data. We try to return a result based on the precision of the inputs. Okay, so we try and exact in, exact out, precision in, some precision out, machine numbers in, machine numbers out. Okay, you can write fast, efficient code by working with large chunks of data. Functions are task or problem based, and I think the two examples I so emphasize that. Functions try to pick a good algorithm based on the problem given. And output from one function can be easily used in other functions, and I kind of, particularly that last example, I hopefully emphasizes that. Okay, and then there's going to be more talks with flashier stuff in numerics coming up. Tomorrow, Wednesday, there's going to be numerical integration with Nina Dokeva, differential and differential algebraic equations on Wednesday at 2, multiphysics modeling with Oliver at 2:30, and finally some application for regions with Oliver and some others on Wednesday. So if you're interested in learning, having more examples of numerical function, those are the talks to go to. But in the meantime, let's go eat. And if anybody wants to ask a quick question, well, I'm willing to answer that.
specify pi before exactly.
You would do n of pi comma 4, but